Welcome. Today I'd like to review some concepts from physics, electrostatics, specifically charge, fields, electrostatic fields, and electrostatic potentials to help you better understand some of the concepts we're learning in our electrochemistry course. So let's start simple. Let's talk about fields and potentials. So I can define a force. We'll define this as an electric force acting on a charged particle. So imagine I have a particle with some charge Q. Okay, so this is a particle with some charge Q. There will be a force acting on that particle if that particle is sitting in an electric field. And that force acting on the particle will be equal to the charge on the particle times the magnitude of the electric field. Now notice these are vectors. So the electric field has a direction and a magnitude. The force has a direction and a magnitude. So I can say that E at a given point, in general this is true for a field, tells you the magnitude and direction of the force a charged particle will feel. Okay? So this charged particle, for example, if it has a positive charge on it, the electric field vector will be in the same direction, the force vector will be the same direction as the electric field vector if Q is positive. So this particle for positive Q will accelerate that direction, and for negative Q it would accelerate the other direction. Okay, so now let's think about force, and we understand how field is related to force, right? So we understand that field basically tells us, electric field, tells us how charged particles, what forces they'll feel in space, given by the electric field. Now, we can also use this concept of electric field to relate to something called potential energy. So in general, potential energy, and I'm sure you've heard this, could be gravitational potential energy. You could have all sorts of different potential energies. There's chemical potential. There's going to be something called electrochemical potential, which we'll talk about. So there's a number of different terms for potentials and potential energies. Today we're going to talk about, in general, a potential energy. Okay, a potential energy. We're going to call this the capacity for a system to do work. Okay, and that's going to arise, which arises from position or configuration. So for example, if I have hydrogen and oxygen mixed together, that system has chemical potential. It could react to form H2O and do work, right? It could heat and expand a gas, it could combust, and that could do work. Here we're going to talk about electrostatic potential energy. So the work, okay, the work we can do is given by the integral, at least in one dimensions. The work that a system can do, we'll call this W, or the work that is done on by a system, is the integral over distance force times dx. So this is the definition of work. So if you think about mechanical work, right? If I have a weight and there's a gravitational force pulling down, mg, right? Then in order to push it up, I have to do work against the gravitational force. And I can calculate the work I do this way. Now, I can also calculate a work electric by just substituting in the term for the force of a charged particle in an electric field. Okay, so there's the electric work done moving a particle with charge q in an electric field over distance. And this is, of course, all in 1D, one dimension. And you can generalize this to 3 dimensions. And we'll show that in a moment for some related equations. So this is the work done. And we said that the potential energy is the capacity for a system to do work. So I can define this as negative delta mu, or let's call this U, delta U, the potential energy from electrostatics. And this is going to be, again, the potential energy change. So it's the change in potential energy of the system. And the negative sign there is because if the system does work, its potential energy goes down. Okay, so you can see the sign there. So we can think about this as potential energy, but what does this mean? What is potential? So this is potential energy. It's an energy, so the units are joules, okay? But now I'm going to define something else. I'm going to define something called a potential, right? So let's do that. So we're going to define something called delta U electric over Q, the charge on a given particle or a test charge, for example. And we're going to say this is phi, the electrostatic potential. Okay. And if I go up to this expression here for the work done, I see that this is in fact simply equal to the integral of the electric field dx, okay? And this is the electrostatic potential. Now, I have chosen this integral to start at x1 and go to x2. Usually, we define phi at x equals infinity equals 0. But there's many other ways to define this. So this is just a reference state, okay? And the electrostatic potential is nothing more than a measure of the work per charge that can be done in moving a particle from a given position x in space to the reference state. So now let's think about how to link electrostatic field E with charge Q and charge density rho. Okay, so Q is going to be in coulombs, rho is going to be in coulombs per centimeter cubed. Okay, something like there, or coulombs per volume, right? So how are we going to do this? And the first way you've learned in the past, I mean, you've all seen this, is something called Coulomb's law. Okay, and what Coulomb's law says, if I have point charges, say I have a positive point charge and a negative point charge, okay, and they're separated by some distance r, okay, and the charge on these is Q1, Q2, I can say that the force between these particles is just Q1, Q2 over 4 pi epsilon naught r squared. So this is the force between those two particles. And I can tell you what these terms are. Epsilon naught is the permittivity of free space. Now, if you decide to apply Coulomb's law with a material that's not vacuum, you want to replace epsilon naught by epsilon of the material, which is equal to epsilon r times epsilon naught, where this is the relative permittivity. So this is going to be typically a number between 1 and 100 times the permittivity of free space. Okay, so this is just the permittivity of free space, just one of those physical constants that nature exhibits that we've determined via experiment that makes this law hold true. Okay, so that's going to be the force between these two particles. Similarly, I can say, well, what if I just have a charge Q? I can say, well, the field due to Q, well, that's just going to be force divided by the second charge. So I could treat Q2 as a test charge, and I could divide the force Q2 would feel in the field of Q1, and I just get Q over 4 pi epsilon naught r squared. Okay, so this is typically the expression you get for the electric field that emanates from a test charge. And it emanates in a spherically symmetric direction, so we only need to consider the radial component of the field. Now, the field points out for a positive test charge, and it points in for a negative test charge. And the reason is because if I think about if I put a charge here, say I put another positive charge here, it would go in the direction of decreasing field. So it would move, it would go along the arrow that the electric field vector points. Okay, so it would move in direction of decreasing potential, not decreasing field necessarily, decreasing potential, and it would go in the direction indicated by the arrow. A negative test charge goes in the opposite direction. It goes against the field lines. And so that's how I remember this sign convention. Now, we can now get the electrostatic potential of a point charge. So again, let's consider a point charge Q. Phi, remember, we define this as sort of the work that would be done by the system in moving a point charge from infinity far away. This is my reference state. Now, but I don't have to choose that as a reference state. Remember, I can choose a different position to have phi equals 0, and we'll do that in one example coming up here, to some position r, and I'm going to integrate the electric field as a function of r. And so one thing that's a little bit tricky here is we have to introduce this negative sign, because I am taking a point charge from here and I'm moving it this direction, right? And for positive Q, the field pushes the other direction. So I've changed my point of reference, basically. So if this is my point of reference, the sign of the field has to switch, because I'm now moving against the field if I have a positive charge and a positive test charge. So that's where the negative sign comes from. The signs in electrostatics are sometimes tedious and sometimes very easy to get it backwards. Okay, so this is the sign, and I can just integrate this expression for the field. Now these are all constants except for r, right? R is the only thing that I need to worry about, so I can bring the rest out. Negative Q 4 pi epsilon naught integral 1 over r squared dr from infinity to r. So integral of 1 over r squared is just going to be 1 over r. So this equals negative Q, or actually the negative will cancel out when I integrate this. It's going to be Q over 4 pi epsilon naught 1 over r from infinity to position r. Okay, and 1 over infinity, of course, is 0, so I just get Q over 4 pi epsilon r. And this is now the potential for a charged particle relative to to 0 at infinity. And I can think about this. If Q is positive and my test charge is positive, right, then my potential is positive as I come in. So I'm actually raising the potential energy of a positive charge, test charge, by moving it closer to the test charge for which we calculated the electrostatic potential distribution for. Okay, so this is again spherically symmetric, and it's just tells you that, you know, as I move a positive charge closer to another positive charge, I got to pay an energy price to do that. Okay, it's really simple. So this is all Coulomb's law. Now let's get a little bit more sophisticated and think about not discrete charges, but charge distributions. For example, a charge density rho instead of a discrete charge Q. Right? Rho is in coulombs per centimeters cubed, for example. So one of the things we need to think about is a concept of flux, okay, a flux of an electric field. So we talked about mass flux, which is sort of, or electron flux, which is species per centimeter squared per area. Well, I can also define a flux of an electric field. And one way you can think about it, okay, is if I have some charge, some arbitrary charge distribution, and I draw a three-dimensional surface around that charge distribution, I can take an area element, okay, call that dA, and I can count, or I can measure how much electric field lines go through that area element, okay? And so the flux is the electric field going through an area. And what's interesting is, if you think about it, if I have a given charge, say a given charge Q, the flux, and we'll call that capital phi here, electric, the flux of the electric field lines is given by Q divided by the permittivity of the medium, epsilon, okay? So this could be epsilon naught if it's a vacuum. And what's interesting about this is, you know, if you think about the amount of field emanating from a given amount of charge, it doesn't matter whether I enclose it in a sphere or a cube or a random shape. As long as it's a completely enclosed three-dimensional volume, the amount of flux will always be related to the amount of charge. And that's what that's saying, is basically a charge gives off a certain amount of electric field, okay? And so the amount of electric field is conserved. It doesn't matter how I enclose that shape. And so this is a formulation of Gauss's law, okay? And we can actually quantify the flux as an integral. So if I take an integral, this is a surface integral, this is what this means, of the electric field dot product with this area element. So I add up how much electric field on these each infinitesimally small area on the surface. I look at the perpendicular component. That's what the dot product does. It gives you the perpendicular component of the electric field to a given surface area, and I add up that all up over the whole surface. I get a measure of the charge, okay? And so this is Gauss's law in integral form, and this is really useful, okay? And I'll show you an example, but this is how one way to go from charge distribution. We'll see different charge distributions. This is just, I should call this Q enclosed. Let's call that Q enclosed, because it's actually the charge, the total charge inside of this volume, right? And, you know, if I had some negative charge in there too, that would cancel out some of the positive charge. So it's the net total charge enclosed in a given volume. And it turns out I can also write this in differential form due to something called the divergence theorem, equals rho, the charge density, over epsilon. Okay, so these are equivalent. This is the differential form of Gauss's law. And you don't need to remember all this stuff. This one's actually pretty useful to remember, that if you just integrate the electric field over the area, you get something related to the charge over the dielectric constant. This is very useful to remember if you can. Okay, so the differential form here is given here, and is this operator del in it. And so del is just a operator from vector calculus that gives us the differential in 3 dimensions. So in Cartesian coordinates, it's this operator. Okay, so it's just taking the gradient of the electric field in 3 dimensions. Now, from Gauss's law, we can actually get something known as the Poisson equation for electrostatics. There's lots of Poisson equations that applies in many types of physics. And I thought I'd show you this very simply because you will see the Poisson equation a lot when you're talking about electrostatics and charge distributions, particularly when you're doing modeling of electrochemical systems. And so I can write the gradient of E is equal to the gradient times the negative gradient of phi, the electrostatic potential. Okay, so this is essentially the derivative of the electrostatic potential gives me the electrostatic field. And this is equal to negative del squared phi, which is equal to rho over epsilon. So this is the form of the Poisson equation that you'll often see. So Poisson takes rho and goes to phi. Gauss's law takes Q enclosed or rho and goes to the electric field. Okay, goes to the electric field. So let's work some examples of this to try to get a better sense of how this works. So one example that's important in electrochemistry, and you'll see over and over again, especially in the discussion of a double layer, right, is the uniformly charged infinite sheet. So an infinite uniformly charged sheet. Okay, so let's draw that. Okay, so imagine I have, a two-dimensional sheet. Now here's just a piece of it, right? Okay, so there's a piece of my sheet, and it goes infinite in all 2 dimensions there. And this sheet has some charge on it, and usually we call surface charge sigma, and this is usually in, for example, coulombs per centimeter squared. Let's put this, define this. This is the surface charge, and this is going to be coulombs per centimeter squared. Now, I could put some positive charges on there just for illustration, but of course the charges can be positive or negative or some combination of the two, and this sigma is going to be the net charge. And then to analyze this with Gauss's law, what we do is we draw a shape to enclose some piece of this surface. So I'm going to draw what's called a pillbox. It's a cylinder, okay? It's a cylinder with some top surface A, and that cylinder is going to go both on the top and on the bottom of this sheet of charge. Now, if I think about the system and the symmetry of the system, I know that the electric field emanating from this sheet of charge must go straight up perpendicular and down perpendicular to the sheet of charge. So if I want to calculate this integral, right, I want to calculate this integral of the electric field times the area, dot product of the area. How do I do that? Well, it's actually really easy in this case because the electric field is completely orthogonal to the area element on this surface. okay? And it's constant over this whole surface. So I can actually take it out of the integral. This is going to have the magnitude of E here, and then the integral over the area. Well, that is just equal to A, okay? So this term here is just going to be EA, but I have to remember that I have A on the top and A on the bottom, okay? So there's field lines going through both, so I better put a factor of 2 in there to account for the top and bottom, okay? And that's just equal to, by Gauss's law, Q over epsilon, and Q is the charge enclosed. So how much charge is there? Well, I know I have some surface charge sigma, which is some coulombs per centimeter squared. So Q is just sigma times the area of the top of the circular area of the pillbox. So this is going to be equal to sigma times area over epsilon. And epsilon is the dielectric constant. So I can find that the electric field now is just sigma divided by 2 epsilon. So that's nice. So the electric field is actually a constant with distance away from the surface, and it points symmetric away or towards, depending if you have positive or negative surface charge, this infinite sheet. Okay, so okay, that's useful. Example. So let's consider now, in an electrochemical context, let's consider a double layer of infinitely charged sheets, like you might find in an electrode surface. So let's draw that. Okay, so I'll draw some negative charge here. Okay, and we know with this negative charge, right, there's going to be an electric field on either side of the negative sheet of charge. And that electric field is going to, if this is the positive x direction, the electric field's going to point towards that sheet of charge, right? So let's draw that. Let's draw that electric field. And its magnitude, right, over here, it's going to be, this is the positive x direction, E, right? E negative equals sigma over 2 epsilon, because it's pointing in the same direction as x, so it's positive. Over here, E negative equals negative sigma over 2 epsilon, because it's pointing in the other direction, right? So the field direction switches when you go across the infinite sheet of charge. Okay, so that would be one sheet of charge. Now let's add a second sheet, and we can do this by superposition, meaning we could just add the two fields from each charge distribution together. Okay, well, this sheet of charge, well, this is going to have field lines going away from the positive charge, because a positive chest charge would be pushed away from a positive sheet of charge. And I can see that on this side, I'm going to have E positive equals negative sigma over 2 epsilon. On this side, E positive equals sigma over 2 epsilon. And so what this shows really nicely is on this side of here, the double layer, these things all cancel out. On this side, they all cancel out too, because the magnitudes are equal and opposite. And the only place the field doesn't cancel is actually in the middle. So if I think about this here, right, you know, these field lines are emanating from the positive charge. These field lines, right, in black, are going all the way to the negative charge. And so they overlap in the middle. And in fact, they're both pointing the same direction. So this arrow and this arrow are both pointing the same direction. So right in between the two, okay, I'm going to have a field equal to sigma over epsilon, right? Because I've added up those two things together. And so that's the field inside of an double layer capacitor. So we can write that E equals sigma over epsilon inside, or between, I should say between, rid of inside, between the sheets, and E equals 0 outside. Okay, so the only place we have a field, right, is right in between the two charged sheets if the charge is equal and opposite. Okay, so now let's think about this in the context of going between charge, fields, and potential. So charge distribution to field to potential. And this is a useful exercise to think through whenever you're thinking about what the electrostatic picture of a given electrochemical system is. So let's draw it. So let's draw rho, the charge density, as a function of x. Now, let's label x equals 0, right? I'm going to have positive charge. Let's put it here, some positive charge here and some negative charge here using my infinite sheets of charge. I'm going to say x is increasing in this direction, and this is 0, and this is some distance d. Okay, and I'll plot d there. So I could represent this on this plot as sort of a line there that represents the positive charge density, and a negative line there that represents the negative charge density. Okay. Now, if I want to go from charge to electric field, I can use Gauss's law or a Poisson equation. I'm basically integrating with some boundary conditions the charge distribution. Okay, so I can integrate this, right? And if I think about it, well, if I integrate this function, then I'm going to get a step function that's going to go step up because there's some charge here. I'll count that charge, and then I'll go across, and then there's the opposite charge, and I'll go back down. And so it turns out that the electric field, and this is exactly what we worked out, the electric field E, function of x, going from 0 to d, is exactly that. It's nothing outside the surface, a step function in the parallel plate capacitor, and then goes back down to 0, and then nothing. And then if I want to go to electrostatic potential, I have to integrate again with a negative sign, and I get the electrostatic potential. And how's that going to look? Well, it's a constant in here, right? And it's 0 elsewhere. So we'll call that phi. It's a function of x, 0, d. Now, the thing about this is I actually have to define where my reference is. And I'm going to define phi at x equals 0 equals 0. Okay, so right there it's 0. Now, I could have defined phi equals 0 anywhere I wanted to. I could have made phi equals 0 the middle of the capacitor, right in the middle. That might be useful for some calculation I was doing. Okay, but I'm going to define it this way. And so outside, because there's no field, if I integrate this function, nothing happens. And then this step function, I start counting the area, right? If I'm integrating this, it's going to be a line. And then it's going to be, again, nothing. And except I forgot to do the negative of the integral. It's going to go down to d and then be flat. Okay. And so that's because phi is the negative integral of e dx. And we can think about that, right? So what would a positive test charge do? Well, a positive test charge should go to lower electrostatic potential. And that's exactly, if I put a positive test charge, what it would do would be accelerated towards the negative charges. So we got the sign picture, right? So this is the electrostatic potential, and it tells you about what a test charge would do and how much work this system can do in moving between any point x here and our reference point where we've defined the potential to be 0. So now you can use this to do, for example, the parallel plate capacitor with electrolyte in the middle, where you have sodium, chlorine, or some other ionized salt, and in that case you polarize, right, and you make double layers at 2 electrodes. You can think about how this picture applies, and this should help you in doing the homework in electrochemistry and understanding more basic physics picture of how electrostatics influences the types of measurements we make and electrochemical systems. Thank you for listening, and I look forward to talking to you again soon.